You know how to find the area of a triangle or rectangle, but how do you find the area under a graph? For example, here I have a portion of, let's say, the x squared graph. So I want to look at this portion of this graph of y equals x squared. And let's just look at the portion that goes from, say, 0 over to 1. What is this area down here? How would I calculate this area? It's not quite a triangle, right? It's curved here, it's not a triangle. That curve isn't the curve of a circle, though. It's no familiar shape that you learned in your high school geometry course. So how could we figure out that area? One way is to try to approximate the area using other shapes that we do know the area of. For example, what we could do is we could break up this area into 4 rectangles, where I'm going to make each rectangle width 1/4. Its total width is 1, so I break it up into 4. I'll have 4 rectangles that are each width 1/4. So here are these 4 rectangles. And notice I designed these rectangles to touch right here at the right endpoint. So I have 4 right endpoint rectangles. Now, the area of these rectangles is not the same as the area of the graph, but it's not so far off. If I found the area of these rectangles, it would give me an approximation of the area under the graph above the x-axis. Let's go ahead and do that. We've already said each rectangle has width 1/4. Right? Each one of these has width 1/4. Because the total width is 1, I divide it into 4 subsections. So for this first rectangle, we know the area is 1/4, and I need to times that by the height of this rectangle. What is the height? Well, I started off at 0, but I went over 1/4, so this is at the x value 1/4, and so the height is the corresponding y value. So that is the x value 1/4. This height here is the corresponding y value, where y is x squared, so the height is 1/4 squared. So just to be clear, for this first rectangle, my width is 1/4, whereas my height is 1/4 squared. Next, I can look at the area of the second rectangle. So let's add to that the area of the second rectangle. It also has width 1/4, but now its height, it's now here, it's gone over once, twice, 2 widths, so it's now 2/4 or 1/2. So its height would be 1/2 squared. Again, plug it into the function to figure out the height. That's the area of the second rectangle. How about the third rectangle? The third rectangle is also width 1/4, but the height of this third rectangle is, if I go over another 1/4, I'm now at, let's get rid of him, that's just a distraction now. I was at 1/2, I go over, and now I'm at 3/4. So his height would be y is x squared, so it's 3/4 squared. 1/2 plus 3/4 squared. And finally, we do it for the last one. The last rectangle is at the x value of 1, so its height is 1 squared, so it's width 1/4 times height 1 squared. So for my 4 right endpoint rectangles, to find the area of these rectangles, I get the area comes out to be whatever the sum is. So sum those all up, and it'll come up to be something around approximately 0.469, I believe. You can double check, sum that up, you get a fraction it's just shy of a half, about 0.469. So what does that tell me? It tells me that my area is approximately 0.469. Okay, that's when I use rectangles with right endpoints. But if you actually look closely at this picture, you'll notice that my area is actually a little bit lower than these. So these 4 rectangles give me an overestimate of the area. I'll call it O for overestimate, O4. An overestimate I got with 4 right rectangles. That overestimate came out to be around 0.469, but it's an overestimate of my area. So my actual area is some value less than 0.469. How much less than? I don't know. Is my actual area 0.2, 0.1? Could it be 0.4? Well, this approximation doesn't tell you. I just know it's less than 0.469. To try to hone in on what the area truly is, we should also try to get a lower bound. Can we get an approximation of the area? So let's draw another figure here, another copy of my graph of y equals x squared from 0 to 1. But now I want to use rectangles that aren't overestimating the area, but are underestimating the area. So what I want to do now is I want to pick rectangles that are within this area, that stay inside of this region. Here my rectangles went out and beyond it. I got extra area. Here I want rectangles to stay inside of the region. So I'll still break it up into 4 subregions. I'll use 4 rectangles again. So I have these 4 subregions. But now I want the rectangles to stay inside. So instead of coming up here and having the right point touch, giving me extra, I'm going to have this left side of the rectangle touch. So this left endpoint will touch. Likewise here I'll go up and have this left endpoint touch. I'll have this left endpoint touch. And this last rectangle, the left endpoint actually touches 0. So it's a rectangle of 0 height. But now I have these 4 rectangles. These are 4 left endpoint rectangles, and they're going to give me an underestimate. They're going to help me figure out what is a lower bound on the area. Just like before, we can calculate the area of these rectangles. Just like before, each of these rectangles has width 1/4. So when I go and I think about the width and the height of my rectangles, each of them will have width 1/4. All of them have width 1/4. But now to figure out the height of the rectangles, this first rectangle, this left endpoint's actually at 0. So it's just 0 squared, which is 0. For the next one, this left endpoint, I'm at 1/4 now. So it's 1/4 squared, so times 1/4 squared. For the next one, I'm now at 1/2 squared, 1/2 squared. And for this last one, I'm at 3/4 squared, 3/4 squared. And I sum those all up, summing up the 4 rectangles. Very similar to before, but here we have a rectangle of 0 height and we don't have a rectangle of height 1 like we had before. So you can see these rectangles will end up being smaller than this sum here because we no longer have this tall rectangle. That one's missing here. You sum these up and we get a sum that I'll denote as U4, an underestimate with 4 rectangles because it's less than the area. And it turns out if you sum these up, you get some number about 0.219. You can sum them up and you get that. Okay, great. So now we know the area between x squared and the x-axis from 0 to 1 is somewhere between 0.219 and 0.469. Pretty good. But that's still a pretty big gap. It could be 0.3, it could be 0.4, it could be 0.25. There's a whole lot of possibilities for what that area is. I want to refine this approximation. How can we do that? Well, the way we're going to do it is instead of using 4 rectangles, I'm going to come back and do this problem again, but double the number of rectangles. So make them each twice as thin. They're going to have width now of 1/8. They're going to have width of 1/8. We'll still keep them right endpoint rectangles, but now have 8 right endpoint rectangles. So here, this right endpoint rectangle will be twice as thin. It's half as thin. And then you have another right endpoint rectangle and another right endpoint rectangle. And hopefully you can see what ends up happening is when you double the number of rectangles, you lose some of this excess area. Before I had all of this area here, when I had 4, but I no longer have that area with 8. Before I had all of this area that I no longer have, extra area. So getting rid of that extra area when I move from 4 to 8 is going to refine my approximation. I still have a little bit of excess. Right here's all extra, right here's all extra, but I don't have as much excess as I had before. And so then you can go through and you can redo this calculation. These each will now have width not of 1/4, but of width 1/8. And so you change these to width 1/8. There'll be 8 rectangles now for you to sum up. But you can calculate that. And you can get that the estimate, still an overestimate, but it'll be a better value now. You sum it up with 8 rectangles. Here, if you want to do it really fast, it's like the first one here, right endpoint, it would be like 1/8 times, you're at 1/8 now. So 1/8 squared plus 1/8 times, the next one would be at 2/8, so 1/4 squared. And you would keep going until you get to the last one, which is here at 1, so it's 1/8 times 1 squared, right? So this is how you calculate 0.8, this overestimate with 8 rectangles. Go ahead and calculate that out, and you get a number that's about 0.398. Okay, so now I know my area is actually less than 0.398. Help me zoom in a little bit. Likewise, in this picture, I can do the exact same thing I did before. Instead of using 4 left endpoint rectangles, I can use 8 left endpoint rectangles. So here, I split this in half, left endpoint rectangle. And notice now, when I use 8, I'm filling up the inside more than I did before. It's still going to be an underestimate, but it's a better underestimate because I filled in some of this inside where it wasn't filled in before. I can go and I can calculate that. I can calculate what is this underestimate with 8 rectangles. So instead of 1/4, these are each 1/8. It would be 0 squared plus 1/8 squared plus 2/8 squared, all the way down through 1/8 times 1 squared, or times 7/8 squared. You sum those all up, and you'll end up with a number that's about 0.273. So by increasing the number of rectangles, you can do the calculation, but the big point we're trying to get here is by using more and more rectangles, both to get overestimates and to get underestimates, we're getting better over and underestimates. We're getting better approximations of our area. Now, one way to approximate the area is you could just take an average of these two. You could say, well, I think the area is somewhere in the middle, and so you can take an average. That would be a good guess. It's not guaranteed to be exactly that average, but it'll give you a ballpark estimate of what the area is. All we can say for sure is the area is somewhere between the underestimate and the overestimate. But still, from 0.27 through 0.398, there's quite a big range there. It could be 0.3, it could be 0.35. There's a lot of things it could be. So what do we do next? You've already guessed it. We're just going to increase the number of rectangles again. So we've done it with 4 rectangles, we've done it with 8. You could double it to 16 or 32. I'm just going to jump right to say 100 rectangles. What do we get if we had 100 rectangles here and we have an underestimate with 100 rectangles? What do we get for my area? Okay, it would be a pain to calculate out. It would be 1 over 100, each width would be 100, times 1 over 100 squared, plus 1 over 100 times 2 over 100, or 1/50th squared, plus 1 over 100 times 3 over 100 squared, all the way down here to 1 over 100 times 1 squared, and that ends up giving you the number something around 0.338. Likewise here, we can do the same thing with 100 rectangles for the underestimate, and we get something around 0.328. Okay. We could go more, we could do 1,000 rectangles, that's getting excessive, but here's the idea. As you increase the number of rectangles, you get better and better estimates of your area, and if you have both overestimates and underestimates, your area is somewhere in between. If you just had one of these estimates, it's still giving you a better idea. Your area is something close to 0.338, but here you can see your area is really getting squeezed in. Your area is somewhere squeezed in between these values. So what do you think the area is? Several things it could be. Maybe it's 0.335, 0.331. What do you think it is? Well, maybe a good guess here is that my area is 1/3. Turns out that's right. But in order to show that the area comes out to be exactly 1/3, you'll need to stay tuned for the next video.